Here is another momentum problem that I made up. I don't know if it's the best. And I'm actually going to add something to it. So the problem states I have a ball of clay with a mass of 50 grams moving with a speed of 2.2 meters per second this way. And then I have another ball of clay, 75 grams, moving with a speed of 3.2 meters per second that way. And they collide. Now, what we know about clay is that clay is going to stick together. So after the collision, I'm going to have two balls of clay, and I don't know which way they're going. I mean, you could guess, right? This one has a greater velocity and mass, so it's going to end up going this way. And we'll call that just V2. So I like to call this A and B. Those are my objects. And then 1, 1, 2. 1 is before the collision, 2 is after. That's just the notation I like to use. And these technically are vectors, but everything's in the x direction. So we're going to treat those as x components of the thing. Now, when we have a situation like this, A is pushing on B, B is pushing back on A, the equal and opposite amounts, that tells us that we can use conservation momentum. However, we have to define our system. The system is A plus B, right? Mass A and mass B added together. Because if you just look at mass A, it's going to go this way and then come back this way with some other speed. It's not going to conserve momentum. It's obviously not. But if I look at the two together, then momentum has to be conserved. So I can write this as P1x is P2x. So the total momentum in the x direction before is the total momentum in the x direction afterwards. The same is true for the y direction, but there's nothing happening in the y direction, so there's no point even writing that down. I mean, maybe there is. I'm not going to do it. Okay, so let's write down what we have. If we're just dealing with momentum, the mass, the units don't matter. So I'm going to leave this in grams. But I'm going to put the g there so we know it's in grams. So P1x, the total momentum before the collision, is going to be this mass times its velocity in the x direction, which is going to be in the positive x direction. So I have, I'm just going to write it out, 50 g grams times its velocity of 2.2. And then this has a velocity in the negative x direction. So it's going to be its mass, 75, that's a 7, g minus 3.2. And that's going to equal the total mass, because now they're stuck together, times their velocity, which would be 50g plus 75g times v2. And I want to solve for v2. That's technically the x component of the velocity. Well, that's pretty easy. I'm going to use the magic of the eraser just because I feel like it. So I can divide both sides by that, and I'm done. And I'm going to add an extra problem, so just hold on. 50 plus 75. Now, I'll tell you why I can write it in grams. Because this is in grams, that's in grams, grams. So I can factor out the grams, divide by grams, the units cancel. Even if I converted to kilograms, I'd get the same answer. So G is a unit there. I don't normally put the units just because I'm lazy. Okay, let's just multiply this out. 50, enter, 2 point, oops, drop, I messed up. I can't really see this too well. 50, enter, 2.2 times. 75, enter, 3.2 times, minus. And then this is going to be 125 divided by. And I get V2 is negative 1.04 meters per second. So it's moving this way. Okay, now let's calculate the change in internal energy for the clay. Now that could be thermal energy, we can include sound, we can include deformation energy, all those kinds of things. So if I again include the system of A plus B, there's no work done on the system, right? Because there's no external forces. So work equals 0, but that's going to be the change in kinetic energy plus the change in, let's just say, generic energy, and that's what we want to find. So the change in energy is going to be negative the change in kinetic energy. So let's find the change in kinetic energy. Let's put over here V2 is negative 1.04. Now I do need to use units of kilograms in this case, because if I want to calculate the energy in joules, the mass isn't going to cancel. So the change in kinetic energy is going to be K2, right? There's only one object, minus Ka1 minus Ka2. This is the initial kinetic energy, 1, Kb1. This is the initial kinetic energy. Why did I put that there? And I'm subtracting it from the final, so it's final minus initial, and that's where they're both negative. So let's put in our values. 1/2. The total mass was 125 grams, or 0.125 kilograms, times the velocity squared. I don't even need to worry about the negative sign, because I'm squaring it. 1.04 squared minus 1/2 mass A, which is 0.05 kilograms, times its velocity of 2.2 meters per second squared, minus 1/2 0.075 times its velocity of 3.2 squared. Now let's put it in our calculator. But I'm going to put it in my calculator because this is my calculator. I'm not going to put it in our calculator. Okay, 0.5, enter. 0.125 times 1.04 squared times, okay, that's that one. Then I have 0.5, enter. 0.05 times 2.2 squared times, and I'm going to subtract those. And then I'm going to do this other one, 0.5, enter. 0.075 times 3.2 squared times minus, and I get negative 0.437 joules. So my change in energy is going to be the opposite of that. So delta E is 0.437 joules. Now, if you wanted to have fun, you could say, well, let's assume that it's clay and all that goes into the change in thermal energy. What's the change in temperature of the things? But I'm not going to do that. That's good enough. It's not elastic because this would be 0. The change in kinetic energy would be 0. Okay, the end.